There is a strange mystery beating beneath every glacier, every ocean swell, every forgotten desert dune, a rhythm so slow and so vast that no ancient storyteller ever sensed it directly. Yet it shaped every climate rise and fall our planet has endured for the last million years. It is the mystery of why Earth cools, freezes, thaws, and warms again in a steady cycle of roughly 100,000 years, a rhythm etched into ice cores, seafloor sediments, and the silent chemistry of ancient atmospheres. And at the center of this mystery lies a quiet, invisible force, the changing shape of Earth's orbit, a soft wobble in the path that carries us around the sun. This story, the one we are about to drift into tonight, traces how that gentle eccentricity, Earth's orbit stretching and relaxing over the ages, became the hidden engine behind the planet's great climatic pulses. For a moment, imagine standing at the edge of Antarctica, the cold air brushing your face, the ice beneath your feet older than the first humans who shaped stones. Beneath that ice lies a record, a perfect timeline showing temperature rises and falls repeating like a heartbeat every 100,000 years. The pattern is unmistakable. Something pushes Earth into deep freeze, then pulls it back toward warmth, not once, but time after time. And it is not random, it is not chaotic, it is a clock. This clock, as modern science eventually learned, is driven by eccentricity, the way Earth's orbit shifts from nearly circular to slightly elliptical over cycles lasting about 100,000 to 120,000 years. That small geometric change alters the distance between Earth and the Sun, nudging the balance of sunlight in subtle but profound ways. When the orbit stretches, the difference between our closest and farthest points from the Sun grows sharper, creating seasons that no longer touch every hemisphere equally. When the orbit rounds again, the contrast softens, sunlight evens out, and the world relaxes its icy grip. For most of human history, these shifts were invisible. Early humans crossing African savannas had no idea their environment was responding to celestial mechanics quietly sliding above their heads. The woolly mammoths roaming Siberia did not know their expansion came from glacial winds triggered by orbital change. The great ice sheets forming across Canada were never aware that each layer of snow they received was part of a cycle older than species themselves. And yet the evidence now whispers the truth. The rhythm is real, steady, and ancient. The narrative you are listening to tonight travels through that rhythm, beginning with the simple fact that Earth's orbit is not fixed. Every 100,000 years, gravitational nudges from Jupiter and Saturn reshape its path just enough to change how sunlight touches the world. That slight distortion, no more than a few percentage points of difference in distance, sets off a cascade of climate reactions. Over millions of years, those cascades carved deserts, built ice caps, drained lake basins, and influenced where humans could live, migrate, settle, and eventually build civilizations. The first part of tonight's journey will gently lay out how eccentricity functions, why an orbit can act like an engine, and how sunlight becomes unevenly distributed across time. We'll look at ice sheets waiting for only a tiny nudge before growing, at feedback loops that amplify small changes into dramatic swings, at oceans storing cold like memories locked deep within currents. As we move forward, the world will shift beneath our feet, tundra spreading, rain belts drifting, lake systems swelling and collapsing under the long pull of Earth's changing ellipse. But before we drift deeper into these immense cycles, it is important to breathe into the atmosphere of wonder that surrounds this entire story. Picture the sun, warm and steady. Picture Earth, gliding gently around it. For all its apparent smoothness, that path is a dynamic, breathing thing. When it stretches, the sun's warmth reaches us in pulses that are stronger in some seasons, yet weaker in others. When it contracts, the warmth becomes more evenly shared across the globe, weakening the contrast that drives ice growth. It is this contrast, the imbalance between summer and winter in different hemispheres, that begins the first quiet steps of an ice age. Strong summers melt snow, weak summers allow it to accumulate year after year. And eccentricity, with its long, deep pulse, decides which of those summers the planet will receive for tens of thousands of years at a time. If this sounds too gentle a force to sculpt continents of ice, remember that Earth's climate responds not only to the amount of sunlight, but to where and when that sunlight arrives. A weak northern summer, repeated for thousands of years, becomes a runway for ice sheets to expand. A stronger summer repeated for thousands more becomes the signal for their collapse. The world breathes in and out, glacial and interglacial, not because the sun changes, but because our orbit does. As we flow deeper into the narrative, you will hear how ice sheets waited like sleeping giants for the right orbital moment to grow, how dust storms thickened across continents when eccentricity weakened monsoons, how oceans stored ancient cold in their depths, and how species, including early humans, shifted their ranges in response to each slow change. You will hear how megalakes rose and fell, how tropical rainbelts wandered north and south, how entire ecosystems appeared and vanished in rhythm with the long curve of Earth's orbital shape. For now, rest in this opening truth. The climate cycles that shaped our past, steered our migrations, sculpted our landscapes, and defined the boundaries of every ancient world were not random. They followed a slow elliptical pulse, a long celestial breath in and out. The eccentricity of Earth's orbit, almost imperceptible in a single human lifespan, was powerful enough to sculpt ice ages, powerful enough to push deserts outward, powerful enough to define where rivers flowed, powerful enough to quietly guide the fate of early civilizations long before they knew what gravity or astronomy even were. And here, at the start of this long story, you can imagine that pulse like a soft, deep drumbeat beneath all of Earth's history. Not loud, not violent, just steady. A rhythm hidden in orbit. The moment Earth's orbit stops being a perfect circle, something subtle but astonishing begins to unfold. An ordinary path around the sun transforms into a climate engine, one capable of pushing the planet toward warmth or plunging it into ice. Even though eccentricity never turns Earth into some wildly elongated ellipse, only shifting from about 0.005 to 0.058 over its full 100,000-year cycle, the effects of that small change ripple outward with immense influence. And because the orbit changes so slowly, the consequences arrive softly, like a long tide, shaping our world not with sudden jolts, but with patient persistence. Tonight, as we drift deeper into this story, we trace how that gentle shift becomes an engine strong enough to set the tempo of Earth's greatest climate rhythms. To understand how this works, picture Earth's orbit from above, almost a circle, but not quite. When eccentricity is low, the distance between Earth at perihelion, its closest point to the Sun, and aphelion, its farthest, barely differs. That means sunlight, the fundamental fuel of climate, is delivered fairly evenly throughout the year. The seasons remain controlled primarily by Earth's 23.5-degree tilt, and glacial cycles depend more heavily on other orbital variations like obliquity and precession. But when eccentricity increases, stretching that orbit outward, perihelion and aphelion drift farther apart. Suddenly, Earth receives noticeably more sunlight at its closest approach and noticeably less at its farthest. Even then, the total annual sunlight barely changes, yet the distribution of that sunlight across seasons shifts just enough to tilt Earth's climate balance. This is where eccentricity quietly becomes an engine, not because it changes how much energy the sun gives, but because it changes when and where that energy strikes hardest. Climate on Earth has always depended less on raw sunlight and more on seasonal contrasts, and eccentricity alters those contrasts like a hand turning a dimmer switch. As the orbit stretches, the precession cycle, the wobble of Earth's axis over 26,000 years, starts interacting with eccentricity in a powerful way. When northern summers occur at perihelion during a high eccentricity phase, sunlight is delivered more intensely, creating strong melts that erode ice sheets. But when northern summers occur at aphelion, that same high eccentricity weakens the summer so drastically that snow can linger year after year, stacking into ice sheets kilometers thick. Scientists often point to this pair, eccentricity enhancing the impact of precession, as the decisive trigger behind the 100,000-year glacial rhythm that began dominating Earth's climate roughly 800,000 years ago. And this reveals an astonishing truth. Eccentricity is the quiet stage on which stronger orbital players act. Without eccentricity increasing or decreasing, the precession cycle alone could not generate such dramatic climate shifts. Eccentricity amplifies climate variability the way a stretched drumhead amplifies the sound of a fingertip. It isn't loud by itself, but it makes everything around it louder. This subtle shift becomes especially important because of the way Earth's surface responds to small, persistent nudges. Ice sheets, for example, are slow giants. They do not react to a warm summer or a cold winter. They respond to 1,000 warm summers or 1,000 weak ones. When eccentricity creates prolonged periods where northern summers receive less sunlight, those summers no longer melt the previous winter's snow. Ice thickens, spreads, and cools the air above it. The planet slowly leans toward a glacial phase. And here's where the orbit becomes an engine rather than a passive shape. Once ice begins to grow, it triggers feedback loops that reinforce the cooling. Vast white surfaces reflect sunlight. Cold oceans absorb more carbon dioxide. Dry air suppresses cloud formation. These feedbacks do not cause eccentricity's power, they magnify it. A small orbital imbalance becomes a full-blown ice age, not because the sun dimmed, but because Earth's climate system amplified the subtle differences eccentricity introduced. The timing matters too. Eccentricity cycles are not all equally strong. Some 100,000-year cycles are shallow, others are deep. Roughly every 400,000 years, a supercycle occurs in which eccentricity reaches especially high values, stretching Earth's orbit far more than usual. These supercycles have historically aligned with some of the most dramatic climatic transitions on the planet, moments when ice sheets advanced across continents or retreated so forcefully that sea levels rose by more than 100 meters in just a few thousand years. During these high eccentricity phases, the contrast between perihelion and aphelion becomes sharp enough to reshape seasonal temperatures. Northern summers may become intensely hot during one part of the cycle and exceptionally weak during the opposite part, pushing Earth toward glacial buildup or collapse with far greater force. It is no coincidence that the last major glacial maximum, the one that covered North America in ice around 21,000 years ago, occurred during a period when eccentricity was higher than it is today. Yet the engine effect becomes even clearer when seen across millions of years. For the first half of the Pleistocene, from about 2.6 million to 1 million years ago, Earth's glacial cycles were dominated by the 40,000-year obliquity rhythm. Ice ages came and went with relatively gentle swings. But then, around 900,000 years ago, Earth shifted into the 100,000-year world, where glacial cycles lengthened, ice sheets grew thicker, and climates swung more dramatically. Why? Because eccentricity began coupling more tightly with precession and ice sheet feedbacks. The orbit's slow stretching and relaxing had finally become strong enough, and the ice sheets large enough, that the climate system locked into this new rhythm. This transition is known as the mid-Pleistocene transition, and it stands as one of the clearest demonstrations that eccentricity can reshape Earth's entire climate architecture. Before the transition, eccentricity's influence was mild. Afterward, its 100,000-year rhythm became the dominant beat of global climate. To imagine how eccentricity acts as an engine, think of a pendulum, one that swings slowly and widely. Each cycle gives Earth a long push toward conditions that either favor ice growth or ice collapse. During low eccentricity, the pendulum narrows, climate swings become gentler, ice ages are less intense. During high eccentricity, the swings widen, the climate becomes more sensitive. Each push carries the planet farther into cold or warmth. Eccentricity also interacts with geography in elegant ways. Because land heats and cools faster than ocean, and because most of Earth's land sits in the northern hemisphere, eccentricity's effect on northern sunlight distribution becomes disproportionately important. That imbalance is why northern summer sunlight is considered the main driver of glacial formation, and it is eccentricity that determines whether those summers are strong enough or weak enough to begin their long march toward an ice age. As this section slows its breath, imagine the orbit not as a fixed track but as a living pathway, one that stretches and relaxes under the pull of giant planets, one that quietly reshapes the fate of ice caps, deserts, forests, and oceans. The engine it forms is not loud, it is not violent, but over 100,000 years it becomes unstoppable. a slow, patient architect of climate. The sun looks constant from where we stand, steady, unwavering, a warm coin hanging in the sky. But when Earth's orbit shifts its shape, the way sunlight touches the planet becomes deeply uneven, and that unevenness becomes the quiet sculptor of every ice age and warm period we have ever known. To understand eccentricity's true power, you have to see sunlight not as a simple brightness, but as a distributed force, one whose timing, intensity, and hemisphere-to-hemisphere delivery determine whether snow melts or survives, whether oceans warm or cool, whether deserts expand or monsoon belts drift. Tonight, we step more deeply into this idea: how Earth's changing orbital eccentricity modifies the sun's touch, making it sharper in some ages, softer in others, and ultimately responsible for the 100,000-year breadth of glacial cycles. When Earth's orbit becomes more elliptical, the difference between perihelion and aphelion intensifies. At its closest approach, Earth receives up to 7% more solar energy than it does at its farthest point, an enormous difference when spread across an entire hemisphere. But what truly matters is not the raw energy, but when that energy arrives. If perihelion aligns with northern summer, that summer burns hotter, melting snowpack, thinning glaciers, and warming high latitudes. But if perihelion occurs during northern winter, the opposite effect takes place. Summers weaken, ice persists, and snow survives long enough to accumulate year after year. This alignment, controlled by the precession cycle, becomes magnified during high eccentricity. In other words, eccentricity acts like a volume knob on the seasonal influence of precession. When eccentricity is low, precession's effect is muted, as if sunlight is spread across the year with relatively even hands. When eccentricity increases, sunlight becomes an uneven painter, highlighting one hemisphere's summers while dampening the others. And this unequal touch of the sun is what begins to pry the planet toward ice or toward warmth. The most important part of this imbalance is northern summer sunlight. Ice sheets grow primarily in the northern hemisphere because that's where most of Earth's landmass resides, land that can hold snow, allow ice to stack, and remain frozen long enough for glacial domes to rise. Oceans absorb heat quickly and release it slowly. Land does the opposite, which is why ice ages ignore the southern hemisphere as the dominant driver, even though Antarctica has its own glacial history. The northern hemisphere's vast continents, particularly North America and Eurasia, are the canvases on which eccentricity paints its climate story. During periods of high eccentricity, when Earth moves much faster through perihelion than aphelion, sunlight becomes squeezed into shorter, more intense bursts during whichever season lines up with Earth's closest approach. If that burst hits northern summer, ice sheets retreat. If it hits northern winter, northern summers become weak and cold, unable to melt the previous winter's snow. That lingering snow becomes reflective, bouncing more sunlight into space, cooling the air above it, and slowly, steadily, initiating a chain reaction that favors ice expansion. This is why scientists often say that sunlight distribution, not sunlight quantity, drives the ice ages. The sun's total output barely changes. Instead, it's the angle, timing, and delivery pattern shaped by orbital geometry that determines which regions of Earth warm enough to melt ice or cool enough to let it accumulate. And eccentricity, quietly and patiently, modulates that pattern like a conductor adjusting the tempo of an orchestra. One of the most fascinating aspects of eccentricity's influence on sunlight is how asymmetrical the seasons become during high eccentricity phases. When Earth follows a stretched orbit, the laws of planetary motion ensure that Earth moves faster when closer to the Sun and slower when farther away. This means that the season occurring near perihelion becomes shorter and more intense, while the season near aphelion becomes longer and gentler. The effect ripples through climate systems like a soft but persistent tug. A short, scorching summer can melt kilometers of ice. A long, cool summer can allow snowpack to linger, perhaps for centuries. This unequal timing doesn't simply warm or cool a year. It rearranges atmospheric circulation patterns. Jet streams shift, monsoons strengthen or weaken, storm tracks migrate poleward or equatorward. The sun's touch becomes a long celestial whisper, reshaping the air itself. One of the clearest examples of sunlight's uneven influence lies in the way high-latitude regions react to small changes in summer insolation. Ice sheets need one thing above all else: summers too weak to melt accumulated snow. When eccentricity suppresses summer sunlight at 65 degrees, a critical latitude used by paleoclimatologists as a climate indicator, ice begins its slow march. The Greenland Ice Core Project, deep-sea sediment cores from the North Atlantic, and oxygen isotope ratios all reveal the same pattern. Glacial periods begin when northern high-latitude summer sunlight drops below a certain threshold. Eccentricity, by modulating precession, creates those thresholds. During times when eccentricity is low, northern summer sunlight varies only slightly, making it harder for ice sheets to either grow massively or collapse catastrophically. That is why low eccentricity periods tend to be climate plateaus, with milder swings between glacial and interglacial conditions. But when eccentricity rises, sunlight delivery becomes dramatically uneven, and Earth's climate begins accelerating toward extremes, thickening ice sheets, deepening cold, then suddenly collapsing those same ice sheets when the orbital alignment reverses. This uneven solar influence also reshapes tropical climates. When the sun's intensity at perihelion strengthens, tropical regions near the equator experience shifts in the intertropical convergence zone, the belt of intense rainfall that migrates seasonally. High eccentricity phases can push this rain belt northward or southward, reorganizing monsoons in Africa, Asia, and South America. Stronger monsoons fill lakes, nourish vegetation, and support animal migrations. Weaker monsoons dry entire continents, encouraging dust storms that further cool the planet by reflecting sunlight. Dust is an important character in this story. During periods when sunlight is unevenly distributed and monsoons weaken, dust levels increase dramatically across northern Africa and Central Asia. These dust clouds reflect sunlight and fertilize ocean waters with iron, stimulating plankton growth that pulls carbon dioxide from the atmosphere. That drop in CO2 cools the world further. And yet, all of it, dust storms, monsoon collapse, plankton blooms, begins with the uneven touch of sunlight during high eccentricity. Even ocean currents respond to the sun's changing distribution. Cold waters sink more easily. Warm waters spread differently. Thermohaline circulation patterns shift, altering global heat transfer. Deep-sea temperatures recorded in benthic foraminiferous shells show unmistakable signatures of eccentricity cycles, matching the timing of sunlight redistribution with remarkable precision. And still, the sun itself remains steady. What changes is how we move around it. As we let this section settle, imagine sunlight as a veil draped around Earth. Some ages pull that veil tight in one corner, others loosen it in another. The result is a patchwork world, some regions bathed in warmth, others starved of it. The unevenness does not roar. It drifts, it leans, it nudges. But over 100,000 years, that gentle redistribution becomes destiny, guiding ice sheets, steering oceans, shifting rain belts, and ultimately determining the shape and fate of the world beneath our feet. Ice sheets do not simply appear, they wait. Across tens of thousands of years, they linger like sleeping giants, gathering strength only when the orbit, the seasons, and the sun's long pulse align in their favor. Tonight, as we drift deeper into the story, we slip into that quiet realm where ice is born. Not in a single winter or decade, but in a slow accumulation of imbalance, a pattern triggered by eccentricity's subtle reshaping of Earth's orbital path. Ice sheets are patient architects. They need weak summers, steady snow, and a world tilted just enough toward cold that each year adds a little more white to the last. In the rhythm of the 100,000-year cycle, eccentricity becomes the hand that opens the door, inviting ice to step forward. To understand how ice sheets prepare to grow, you must first see how delicate the balance truly is. Snowfall alone does not create glaciers. Snow must survive the summer melt. At high latitudes, especially near the key threshold of 65 degrees, summer insolation dictates everything. If sunlight remains strong enough for long enough, even a large winter snowpack will vanish. But if summer sunlight weakens just slightly year after year, snow begins to linger through September, then October, then through the first snows of the next winter. In this moment of lingering, ice is born. This is why eccentricity's influence is so decisive. During periods of high eccentricity, when northern summers align with Earth's farthest distance from the sun, summer warmth becomes weaker, softer, more subdued. Snow no longer melts completely. Small ice patches remain. Those patches reflect more sunlight, cooling the air above them and allowing even more snow to survive the following summer. The cycle repeats with slow confidence. Over centuries, thin ice becomes thick ice. Over millennia, that thick ice becomes a dome. Over tens of millennia, that dome grows into the Laurentide ice sheet or the Eurasian ice sheet, vast bodies of frozen water larger than entire modern continents. Geological evidence supports this slow awakening. Cores drilled deep into the Greenland ice sheet show layers dating back hundreds of thousands of years, revealing moments when ice growth surged rapidly after long periods of calm. Similarly, North Atlantic sediment cores reveal pulses of cold freshwater entering the ocean, each corresponding with major expansions of northern glaciers. These are not chaotic events, they occur in rhythm with eccentricity cycles. The timing is too perfect to be coincidence. At the heart of these expansions is Earth's albedo feedback, one of the climate system's most powerful amplifiers. Fresh snow is brilliant white, reflecting up to 90% of incoming sunlight. Even small accumulations cool the surface dramatically. As eccentricity weakens northern summers, those reflective patches expand, turning regions that once absorbed summer heat into bright, cold mirrors. The feedback loop grows. More reflection means colder summers. Colder summers mean more snow survival. More snow survival means more ice, and more ice means even greater reflection. A runaway but gentle cascade builds the foundations of an ice age. Yet, ice sheets do not grow everywhere with equal enthusiasm. Geography shapes their ambition. North America's broad, flat interior, stretching from present-day Minnesota through Canada to the Arctic, creates a perfect staging ground for massive ice formation. Snow accumulates on lands tilted slightly toward the pole, sheltered from strong oceanic warmth and buffered by high mountain ranges. Eurasia has similar features. In contrast, regions like Alaska remain surprisingly ice-free during peak glacial periods because the surrounding ocean delivers enough warmth to prevent persistent snow cover. Eccentricity may set the conditions, but geography decides where the giants rise. When eccentricity stretches Earth's orbit significantly, winter becomes longer when Earth is far from the sun. During these long winters, snowfall increases, particularly over northern continents. Meanwhile, summers located near aphelion receive less intense sunlight. This double effect, more winter snow, weaker summer melt, creates the first footholds for ice expansion. As ice spreads, it modifies wind patterns. Cold, dense air sinks over the growing ice sheets, pushing atmospheric circulation southward. Storm tracks shift, precipitation patterns change. Deserts expand in some regions while snowfall intensifies in others. These changes reinforce ice growth, all beginning with eccentricity's quiet pull. Ice cores from Antarctica reveal synchronized yet asymmetrical responses. While the northern hemisphere drives the initiation of glacial cycles, the southern hemisphere often responds later, not because eccentricity acts differently there, but because Antarctic ice sheets are already well established and the Southern Ocean moderates temperature shifts. Still, the South cools as carbon dioxide levels drop, another part of the feedback loop triggered by northern ice growth. The planet, though asymmetrical, dances to a single eccentric rhythm. Interestingly, ice sheets do not grow steadily. They advance in pulses, periods of rapid accumulation separated by intervals of relative calm. This pulsing reflects interactions between eccentricity, precession, and obliquity. A slight shift in Earth's tilt can strengthen summer sunlight again, slowing ice growth until the next eccentricity-driven window of weak summers arrives. These pauses explain why some glacial periods contain internal fluctuations, cold phases within cold phases, minor retreats before massive advances. Ice listens to the combined music of orbital cycles, not just one. Once ice sheets reach a critical size, spanning thousands of kilometers, they begin to shape the planet physically. Their immense weight depresses the crust beneath them, lowering the land by hundreds of meters. As the crust sinks, new regions fall into colder air layers, allowing snow to accumulate more easily. Deep valleys form around the edges. Glacial rivers carry fine powder across continents. Winds sweep that powder into enormous loess fields in China, Europe, and the American Midwest. These sediments today form some of the richest agricultural soils in the world, a quiet legacy of eccentricity-driven ice growth. Another powerful factor is ocean circulation. When ice expands, global sea level drops, sometimes by more than 120 meters. This exposes continental shelves, creating new land bridges like Beringia, linking Siberia and Alaska. Ocean currents reroute around these newly shaped coastlines, intensifying cold deepwater formation in the North Atlantic. The deep ocean cools, storing the signature of eccentricity in its temperature layers. Evidence from benthic foraminifera reveals that every major cooling event matches a phase when eccentricity enhances the impact of weak northern summers. And so the waiting ends. What begins as a whisper of imbalance, a slightly weaker summer here, a longer winter there, slowly awakens a frozen force capable of reshaping continents. Eccentricity does not command the ice directly. It simply tips the balance, gently at first, then decisively. Ice sheets grow, not because Earth desires cold, but because the orbit invites it. Now, imagine standing on the edge of a forming ice sheet. It is not dramatic. It is quiet. Snow lies deeper than last year, and deeper still the next. A wind sweeps across a widening field of white. The sun hangs lower. The summers feel shorter, softer. Beneath your feet, ice begins its ancient rise. It waits for the right orbital moment, and then slowly, inevitably, it grows. There is a precise moment, subtle, almost invisible, when Earth crosses a climatic threshold so delicate that even a slight shift in orbital geometry can tip the entire planet from warmth toward ice. This moment is not a dramatic plunge. It is a quiet crossing, like placing one final grain of sand on a scale already near balance. For tens of thousands of years, eccentricity slowly reshapes Earth's orbit, adjusting the contrast between seasons, softening northern summers, lengthening winters. Snow begins to linger, ice forms footholds. But none of this guarantees the start of a full glacial period. The world can hover in a state of almost ice, teetering just shy of a runaway freeze, until eccentricity and precession align with just the right tilt. Tonight's part of the story explains that fragile edge, the triggering threshold that determines when small orbital nudges finally cascade into a full ice age. Scientists searching for this threshold found its signature not in the atmosphere, but in the sediments of the deep sea. Drilling into the ocean floor off Greenland, Antarctica, and the North Atlantic, researchers discovered rhythmic layers of tiny foraminiferous shells, each layer preserving temperature information from millions of years past. These shells record the oxygen isotopes from seawater, which shift depending on how much ice exists on land at any given time. The patterns were unmistakable. Sharp transitions from warm to cold states occurred only when northern summer insolation dropped below a critical threshold, specifically around 460 to 480 watts per square meter at 65 degrees N. Above that value, ice could form locally but never expand aggressively. Below it, ice accumulation surged. This threshold, identified in the 1970s and refined through modern climate models, marks the point at which summer warmth becomes too weak to overcome winter snowfall. But eccentricity alone does not create this threshold. It sets the stage. Precession provides the timing. Obliquity, Earth's 40-once-a-year tilt cycle, determines the angle at which sunlight strikes high latitudes. When all three cycles align to reduce northern midsummer sunlight below the threshold for thousands of consecutive years, the world tips. Think of it like three keys turning in a lock. Eccentricity stretches Earth's orbit. Precession positions northern summer at aphelion. Obliquity dips slightly lower than average, shading high latitudes. When these conditions overlap, even slightly, Earth's climate gently crosses the threshold. And once crossed, feedback loops begin to take over, pushing the planet deeper into cold. One of the most important of these feedbacks involves the snow line, the elevation where seasonal snow persists year-round. During periods of strong sunlight, the snow line retreats into the mountains. But when summers weaken, the snowline descends, expanding across plains and plateaus. Once snow persists at lower elevations, it increases Earth's albedo dramatically. More reflection means less absorbed heat. Less heat means more snow survival. And because eccentricity can suppress summer insolation for tens of thousands of years, the snowline can keep sliding downward until enormous ice sheets begin to grow. Models show that when summer insolation drops just 2 to 3% below modern levels over the course of several millennia, ice sheets suddenly shift from stable to advancing. This tiny change is astonishingly effective. If Earth's orbit delivers slightly weaker sunlight over Greenland for 8 or 9,000 years in a row, the island stops functioning like a northern buffer and begins acting like a glacial pump, producing cold air masses that drift south and seed further ice formation. This threshold crossing is visible in one of the most dramatic datasets on Earth, the Vostok and Epica ice cores from Antarctica. These ice cores, stretching back more than 800,000 years, show repeated glacial inceptions marked by a tight interplay between CO2, temperature, and eccentricity-modulated insolation. Every glacial cycle begins when eccentricity pushes the northern summer insolation below the magic threshold. CO2 begins to fall shortly afterward, not as a cause but as an amplifier. When ice sheets grow, oceans cool. Cold water absorbs more carbon dioxide. The atmosphere loses greenhouse gases. Temperatures drop further. Weak sunlight plus lower CO2 levels become the quiet duo that locks the planet into its icy state. It isn't a single switch, but an unfolding. First, the orbit tilts the balance. Then, feedbacks reinforce the tilt. Crossing the threshold also affects weather patterns. As ice accumulates, the jet stream shifts southward, storm tracks reorganize, continental interiors dry out, drought stretches across the subtropics, dust storms intensify, especially in North Africa, Central Asia, and the American West. This dust cools Earth further by reflecting sunlight and fertilizing iron-poor ocean regions. Plankton blooms proliferate, drawing even more CO2 out of the atmosphere. And yet, all these changes begin from that initial orbital threshold, eccentricity pushing summers just weak enough that snow no longer melts. The most striking evidence for threshold-triggered glacial inceptions appears during the mid-Pleistocene transition, roughly 900,000 to 600,000 years ago. Before this period, Earth repeatedly crossed the insolation threshold every 41,000 years due to obliquity changes, leading to relatively modest glacial cycles. But around 900,000 years ago, ice sheets became larger and more persistent. Their thickness reached a new state, one that allowed them to survive mild interglacial periods. Once the ice sheets grew tall enough, they created their own microclimates, reinforcing the cold. At this point, eccentricity's 100,000-year cycle became dominant. The threshold became harder to cross, requiring longer periods of weak sunlight. Once crossed, the resulting glaciations became far deeper and longer lasting. This shift gives us insight into the complexity of the threshold. It is not static. It moves slightly depending on geography, sea levels, greenhouse gas concentrations, and ice sheet height. In some cycles, Earth enters a glacial period only when eccentricity is high enough to amplify precession strongly. In others, even moderate eccentricity can be enough when combined with a decrease in CO2. The threshold behaves like a boundary of probabilities rather than a strict switch, but its influence is unmistakable. Perhaps the most remarkable aspect of this threshold is how quietly it operates. There is no moment when Earth suddenly freezes. A person living 100,000 years ago, watching snow linger a few weeks longer each year, would never suspect that an ice age tipped forward because of a subtle geometric shift in Earth's orbit. No ancient hunter in Eurasia would feel the crossing, no mammoth herds would sense the beginning. But glaciers would begin to spread, valleys would fill with ice, rivers would shift, forests would retreat, grasslands would expand. And over a few thousand years, barely noticeable in geological time, the world would transform. Imagine walking across a forested landscape in northern Canada during one of these moments, perhaps 120,000 years ago. The summer sun feels weaker, though you cannot say why. Snow at the top of a distant ridge remains into autumn, By the next generation, that ridge is white year-round. By the next millennium, the white crest has extended down the slope, then onto the plains, then toward the horizon. The ice sheet has begun, all because eccentricity has eased the sun's touch, tipping Earth below its climatic threshold. And once that threshold is crossed, there is no quick reversal. The world must wait until the orbit shifts again, until eccentricity decreases, until precession swings back, until northern summers strengthen once more. Only then, tens of thousands of years later, does the ice retreat. A long, patient threshold, a small imbalance, a world transformed. Heat does not travel evenly across a world whose orbit stretches and breathes through ages. When eccentricity increases, the rhythm of sunlight grows uneven, and the seasons begin to warp in ways that quietly reshape the climate for tens of thousands of years. It is one of the strangest features of celestial mechanics. Earth does not move around the sun at a constant speed. When it is closer, it races forward. When it is farther, it drifts more slowly. This alone means that one hemisphere will always experience a shorter, more intense season, while the opposite one endures something longer and gentler. And when eccentricity is high, that asymmetry becomes extreme. Tonight, we follow that slow distortion, this unequal distribution of heat, and watch how it becomes the next great force guiding Earth into deeper ice or lifting it out again. To appreciate how season length changes, imagine Earth's orbit stretched into an ellipse. Near perihelion, Earth sweeps through its closest point quickly. A season that coincides with perihelion ends up short but intense. Near aphelion, Earth lingers, and the corresponding season becomes long but mild. Even though the sun's total energy output barely shifts across millennia, this simple difference in timing alters the climate profoundly. During periods of low eccentricity, the seasonal asymmetry is minor. But when eccentricity increases, the contrast sharpens dramatically. The short season becomes briefer and brighter, the long season becomes longer and dimmer. This timing effect is central to how glaciations rise and fall. If northern summer aligns with perihelion during a high eccentricity phase, that summer becomes intense enough to melt lingering snow, weakening ice sheets. But if northern summer arrives near aphelion, during the long, cool stretch of Earth's orbit, summer warmth weakens for thousands of consecutive years. Snow stops melting, ice sheets breathe in, the planet begins to cool, and all of this unfolds whether a single human notices or not. Earth's orbital mechanics, described by Johannes Kepler centuries ago, reveal the speed variation with stunning clarity. As Earth nears the Sun, gravitational pull increases its orbital velocity. It moves fastest at perihelion, currently in early January, and slowest at aphelion, in early July. During high eccentricity phases, that speed difference becomes great enough to distort the calendar of seasons themselves. Winters in the hemisphere that experiences aphelion become long, dark, and cold. Summers arriving at aphelion are long but weak. And the hemisphere experiencing perihelion receives very short but intense heat bursts that concentrate energy into a compressed interval. This heat compression plays a major role in melting ice sheets. A short, scorching summer might melt vast areas of snow in Canada or Siberia. But if eccentricity suppresses that summer by shifting it away from perihelion, heat no longer arrives in strong enough pulses. The world begins to tilt toward ice. One of the clearest pieces of evidence for this seasonal asymmetry comes from the paleoclimate record. Deep-sea sediment cores from the Indian Ocean and the South Atlantic show that during periods of high eccentricity, the seasonal contrast in the northern hemisphere becomes noticeably exaggerated. Oxygen isotope ratios indicate deeper winter cooling and more persistent summer snow. Meanwhile, monsoon records, especially from Africa and Asia, show that rainfall patterns swing more wildly, tracking the shifting intensity of sunlight. When Earth's orbit elongates, heat arrives unevenly, but moisture distribution shifts as well. The hemisphere receiving a short, intense summer tends to experience stronger monsoons because intense summer sunlight heats the land quickly, drawing moist air from the oceans. But in the opposite hemisphere, the long, weak summer suppresses monsoon circulation, drying out entire regions. This is why eccentricity cycles appear prominently in ancient lake sediments from East Africa, Arabia, and India. Lake levels rise and fall in a repeating rhythm tied not solely to rainfall, but to the overall redistribution of sunlight shaped by eccentricity. This redistribution affects wind patterns too. Jet streams strengthen or weaken depending on the contrast between fast heating and slow heating regions. During high eccentricity, the hemisphere with a compressed summer tends to generate stronger temperature gradients, intensifying mid-latitude storm tracks. Meanwhile, the opposite hemisphere drifts into long periods of stability, dryness, and dust. The Sahara, for example, becomes significantly dustier during weak northern summers. These dust pulses coincide with eccentricity maxima in marine sediment cores collected off northwest Africa. Among the most intriguing consequences of seasonal asymmetry is its impact on ocean circulation. Oceans respond slowly to uneven heating. When warm seasons become short and intense, surface waters heat quickly in one hemisphere, strengthening evaporation and altering salinity. Meanwhile, the opposite hemisphere receives more prolonged seasons of gentle cooling. This imbalance can shift deep water formation zones in the North Atlantic. Paleoceanographic data shows that the strength of the Atlantic meridional overturning circulation oscillates with eccentricity cycles, becoming stronger when northern summers are intense and weaker when northern summers weaken. These shifts redistribute heat worldwide and leave chemical fingerprints throughout the deep ocean. In surface ecosystems, seasonal asymmetry affects vegetation patterns. During long, cool summers, forests retreat southward, while in short, intense summers, boreal forests expand rapidly. Grasslands appear or disappear depending on how evenly heat spreads through the growing season. Fossil pollen records from Europe and Siberia show abrupt reorganizations of plant communities timed perfectly with eccentricity-driven shifts in seasonal intensity. This also influences ice formation. A long, dim summer cannot melt the previous winter's snow, and a long, cold winter only makes the snowpack thicker. Over thousands of years, the imbalance becomes structural. Snow accumulates earlier in autumn, persists longer in spring, and gradually compresses into firn and then into blue ice. The ice sheet begins to advance. Minor changes in insolation become major changes in Earth's reflectivity. The unevenness of solar delivery becomes a blueprint for ice. Eccentricity also interacts with volcanic cycles indirectly through its influence on stress patterns in glacial regions. When ice sheets grow asymmetrically, expanding more in some regions and less in others, Earth's crust experiences shifts in pressure. These shifts can influence volcanic activity, particularly in tectonically sensitive regions like Iceland. Studies of volcanic ash layers show several correlations between enhanced glaciation during high eccentricity phases and increased volcanic events. These eruptions can further cool the climate by adding sulfate aerosols to the atmosphere, deepening the cooling trend. Perhaps the most unexpected consequence of uneven seasons lies in the way ecosystems migrate. Animal migrations depend on the timing of heat, food availability, and rainfall patterns, all of which shift during high eccentricity. Large mammals such as woolly mammoths and steppe bison migrated across Eurasia in patterns that match eccentricity cycles recorded in sedimentary deposits. During long, cool summers, grasslands expanded, providing abundant forage. During short, intense summers, forests reclaimed land and pushed herbivores toward colder regions. These migrations shaped predator populations, human hunting strategies, and even the early movements of human ancestors. Uneven seasons also influenced the spread of humans. During periods of strong northern summers, regions like Siberia and Alaska became more accessible, their snowpack melting earlier and vegetation greening sooner. But during long, weak summers, these same regions became inhospitable, pushing human groups southward or trapping them in environmental bottlenecks where archaeological traces remain to this day. As we let this section soften, imagine the world breathing through uneven seasons. One hemisphere feels warmth compressed into a bright, fleeting pulse. The other receives it stretched thin across a long, cool span. Ice waits for these moments. Forests respond to them, winds follow them, oceans remember them. Heat never arrives evenly, not when the orbit stretches, not when the path bends. In this slow swing of sunlight across ages, the seeds of ice and warmth find their turning points. And as the orbit changes shape, Earth's seasons tilt again, quietly reshaping the destiny of every continent. A planet does not simply fall into cold and then leap back into warmth. It breathes. Across the long arc of Earth's history, the world inhales ice and exhales warmth in cycles so vast that no single generation could ever witness their rise or decline. And at the quiet core of this rhythm lies eccentricity, Earth's orbit stretching and relaxing, tightening and loosening over spans of 100,000 years. This subtle change becomes the deep pulse behind Earth's glacial breathing, guiding the expansions and retreats of ice sheets, the shifts in ocean currents, the wandering of deserts, and the long oscillation of climate systems. Tonight, we enter that slow pulse, this planetary breath, and watch how eccentricity gives it shape. To imagine this breathing, look to the glacial cycles themselves. Ice sheets grow over roughly 80,000 to 90,000 years, then collapse in a sudden exhalation lasting only 8,000 to 12,000 years. The pattern is asymmetrical, slow build, rapid melt. This asymmetry puzzled early climate scientists until they began to examine the orbital cycles controlling northern summer sunlight. During high eccentricity phases, when northern summers weaken for thousands of years at a time, ice accumulation becomes almost inevitable. Winter after winter, snow piles up. Summer after summer, it fails to melt. The world inhales. But eventually, eccentricity shifts. The orbit relaxes. Precession aligns northern summers with perihelion. Sunlight strikes the high latitudes with renewed intensity. And in a geological instant, after tens of millennia of quiet buildup, the ice sheets collapse. Meltwater floods the oceans, sea levels rise by more than 100 meters, coastlines redraw themselves, forests migrate, rivers carve new paths, the world exhales. This breath is recorded in every major paleoclimate archive. If you take a cross-section of the Greenland ice sheet, each layer of trapped snow and dust tells the same story. Long stretches of cooling punctuated by abrupt warm periods known as interglacials. If you examine the deep ocean sediments, the oxygen isotopes show glacial expansion and retreat in perfect 100,000-year rhythm. Even cave formations, stalagmites and stalactites, carry the signature of Earth's breath. Their growth rates accelerate during warm, wet periods and slow during cold, dry ones. All of these archives beat to the same orbital drum. One of the most fascinating elements of this long breath lies in the way ice sheets behave once they reach massive sizes. During their growth, the process feels patient and inevitable. But once ice covers millions of square kilometers, the world becomes exquisitely sensitive to small solar changes. Even modest increases in northern summer insolation, driven by eccentricity-enhancing precession, can destabilize an ice sheet's edges. Meltwater flows beneath the ice, lubricating its base, allowing glaciers to slide more quickly toward the sea. This process, combined with rising temperatures, initiates the dramatic exhalation phase. This behavior is captured beautifully in marine sediment cores, showing Heinrich events, episodes where huge armadas of icebergs broke away from the Laurentide ice sheet and drifted across the North Atlantic. These events occur during intervals of climatic instability, often when eccentricity is beginning to weaken its hold and sunlight strengthens. Icebergs pour into the ocean, depositing layers of rock and sand far from their origin. Each layer marks a breath in the cycle. Another remarkable dimension of Earth's breathing lies in deep ocean circulation. During glacial expansions, cold water sinks more efficiently in the North Atlantic, strengthening the global conveyor belt known as the Atlantic Meridional Overturning Circulation, AMOC. This circulation pulls warm water northward, but during ice buildup, the cold surface waters suppress its strength, deepening global cooling. When meltwater floods the ocean during deglaciation, the fresh water disrupts density-driven sinking, weakening the AMOC and reshaping heat distribution around the world. Eccentricity does not directly change the AMOC, but its control over ice sheets does. And the oceans carry this signature for thousands of years. The planet's breath can also be traced in atmospheric chemistry. During glacial buildup, the cooling oceans absorb more carbon dioxide. During deglaciation, the warming oceans release CO2 back into the air. Ice core records from Antarctica show CO2 levels oscillating between around 180 parts per million in glacial maxima and around 280 during warm interglacials. These atmospheric changes amplify eccentricity's pacing. Once the ice begins to collapse, rising CO2 accelerates the warming. Once ice begins to grow, falling CO2 reinforces the cooling. The breath becomes self-sustaining. Dust is another participant in this grand rhythm. During glacial expansions, deserts grow across Africa and Asia as monsoon systems weaken. Winds sweep vast quantities of dust into the atmosphere and across the oceans. This dust settles on the ocean surface, fertilizing plankton blooms which then draw down more CO2. When deglaciation begins, rainfall increases, deserts shrink, and dust storms weaken. The atmosphere clears. Darker oceans absorb more heat. The breath exhaled. This cycle of dust, CO2, ice, and temperature, each tied to eccentricity's modulation of sunlight, forms a stable but dynamic climate engine. Scientists working on the paleoclimate histories of the Tibetan Plateau, the Sahara, and Australia have discovered that dust layers correlate precisely with eccentricity maxima. During times of high eccentricity, when summers weaken, dust pulses become pronounced. During low eccentricity, when seasons become more even, dust levels fall. The Earth breathes in dust during glaciation and exhales it during warmth. The 100,000-year cycle also shapes rainfall patterns across the tropics. The intertropical convergence zone, the great belt of rain that follows the sun seasonally, shifts north and south depending on hemispheric heating. During glacial expansions, cooling in the northern hemisphere pushes the rain belt southward, drying northern Africa and southern Europe. When deglaciation begins, the rain belt drifts north, turning parts of the Sahara into grassland and lakes. This pattern repeats with astonishing consistency, visible in ancient lake shorelines, river channels, and pollen records. With each breath, the tropics shift, feeding back into global climate systems. Earth's breath is not confined to ice and water, it also shapes life. During glacial maxima, species migrate southward as cold expands across continents. During interglacials, life spreads northward again. Entire biomes, forests, grasslands, tundra, pulse with the cycle. Fossil pollen records from Europe show forests retreating into southern refuges during glaciations, then surging north as warmth returns. In North America, animals traveled across the Bering Land Bridge during cold periods when sea level fell, only to retreat when meltwater submerged the corridor again. Human ancestors felt this breath too. Though they could not name eccentricity or orbital cycles, they moved with the world's exhalations, following grasslands, avoiding ice, discovering new routes only when the planet's warmth returned. Their migrations, survival strategies, and early dispersals were shaped by this slow climatic tide. And at the center of it all is a single elegant truth. Eccentricity guides the timing. It does not force the climate, it nudges it. It sets the length of each inhalation and exhalation. It gives Earth its long, steady pulse. As this section fades, imagine standing at the edge of an ancient glacier. You hear nothing. You feel nothing. Yet the world around you is breathing. Inhale, ice growing. Exhale, ice retreating. And above you, in silence, the orbit shifts, beginning the next long breath in Earth's ancient rhythm. Far below the rolling waves and drifting continents, farther still beneath the reach of storms, winds, and surface currents, the deep ocean holds memories that last far longer than civilizations. These cold waters, dense, dark, and slow, form the most ancient archive on Earth, preserving the signature of every glacial cycle and every shift in orbital mechanics. They are the silent chroniclers of eccentricity's long rhythm, recording changes in temperature, chemistry, and circulation that echo the climate transformations happening above. Tonight, we descend into that oceanic memory, the slow pulse of deep water that remembers the cold for tens of thousands of years, and discover how the ocean becomes an essential link between eccentricity and Earth's 100,000-year climate cycles. To understand the ocean's memory, imagine the great conveyor belt of global circulation. often called the thermohaline circulation or the global overturning system. Warm surface waters drift northward in the Atlantic, cool as they approach the Arctic, and sink into the abyss, beginning a centuries-long journey southward along the ocean floor. These deep waters move sluggishly, taking up to 1,000 years to complete their loop through the global ocean. Because they travel so slowly and stay insulated from sunlight, their temperatures and carbon content reflect conditions from the time they first sank. Every pulse of cold that reaches the surface, every change in sea ice, every shift in atmospheric CO2, it all becomes locked into these deep waters like a diary entry waiting to resurface centuries later. When eccentricity begins to weaken northern summers, ice sheets expand. As snow accumulates and glaciers thicken, the atmosphere cools. Cold winds sweep across the North Atlantic, cooling surface waters more rapidly. This cooling increases the density of seawater, causing it to sink more efficiently. Each sinking event sends a pulse of cold into the deep ocean. Over centuries, these pulses accumulate, lowering deep ocean temperatures globally. When scientists drilled into sediment cores at depths of 4,000 or 5,000 meters, they found evidence of these pulses. Oxygen isotope ratios in the shells of benthic foraminifera shifted toward heavier values, indicating colder, more iceberg-influenced waters during glacial buildup. These isotopes form a repeating pattern that mirrors eccentricity's pacing with astonishing accuracy. Yet the ocean does more than store temperature. It stores carbon. During glacial expansions, strong winds over newly exposed continental shelves create vast dust storms that fertilize the surface ocean. Iron-rich dust increases plankton productivity, especially in the Southern Ocean, where iron is often scarce. As plankton grow and die, they sink, transporting carbon from the atmosphere into the deep sea. This process, known as the biological pump, draws down atmospheric CO2 by 20 to 30% during glaciations. The timing of these CO2 declines, captured in Antarctic ice cores, aligns perfectly with eccentricity-driven weakening of northern summer sunlight. The deep ocean becomes a vault of dissolved carbon. As surface waters grow colder and sink, they trap CO2 in the abyss for thousands of years. The ocean remembers the cold not only in temperature, but in chemistry. High-latitude cooling, initiated by eccentricity's redistribution of sunlight, therefore sets up a long-lasting cascade. Weaker summers, more snow, larger ice sheets, colder oceans, reduced CO2, more cooling. The deep ocean becomes both witness and accomplice. One of the most striking demonstrations of this oceanic memory lies in the difference between glacial and interglacial ocean structure. During glacial maxima, the deep ocean becomes poorly ventilated. In other words, the cold water that sinks at high latitudes stays trapped, circulating slowly along the sea floor, accumulating carbon and nutrients. These old waters become enriched in carbon dioxide, making them heavy and stable. Above them, surface waters grow lighter and fresher due to increased sea ice and reduced evaporation. This stratification acts like a lid, preventing the deep carbon reservoir from mixing upward. It is only when eccentricity shifts and northern summer insulation strengthens, initiating deglaciation, that this structure breaks down. As the ice sheets begin to melt, freshwater floods into the North Atlantic. This freshwater is less dense than salty seawater, weakening deep water formation. Without sinking waters to replenish the deep ocean, the carbon-rich abyss begins to well upward. Oceanographers have found evidence of this in abrupt increases in atmospheric CO2 at the end of glacial periods, rises of 50 to 80 parts per million within a few thousand years. These rises coincide with periods when eccentricity and precession increased northern summer sunlight, causing ice sheets to melt rapidly. The deep ocean remembers the cold for millennia, and when the orbit shifts, it exhales that memory back into the atmosphere. But the ocean's role in eccentricity-driven climate cycles extends beyond carbon. It also regulates heat storage. During glacial buildup, the colder deep oceans store vast amounts of thermal energy by removing it from the atmosphere. During deglaciation, the release of warmer deep waters back toward the surface helps accelerate global warming. This process helps explain why interglacial periods arrive so quickly, because the ocean, once triggered by orbital changes, rapidly returns stored heat to the atmosphere. Paleoceanographers studying the Southern Ocean discovered another crucial link: the formation of Antarctic bottom water, the coldest and densest water mass on Earth. During glacial periods, when sea ice expands and winds shift, Antarctic bottom water formation intensifies. Colder water sinks more vigorously, strengthening global deep ocean circulation. This enhanced circulation pulls more carbon into the deep ocean and spreads cold across the world. The intensity of this circulation varies in near-perfect phase with eccentricity cycles, proving that the ocean is not merely responding to climate, it is amplifying it. In the North Pacific, sediment cores reveal similar rhythmic changes. Although the Pacific does not form deep water in the same way the Atlantic does, changes in oxygen content reveal how ventilation varied across glacial cycles. During eccentricity maxima, when northern summers weaken and ice expands, Pacific deep waters become depleted in oxygen, indicating sluggish circulation and long isolation. During deglaciation, oxygen levels suddenly rise as fresh, warmer waters begin to ventilate the basin again. These shifts match the timing of ice sheet expansions and collapses, driven by eccentricity-modulated insulation. The deep ocean also influences sea level changes. During glaciations, as more water becomes locked into ice sheets, sea levels fall by up to 120 meters. This exposes continental shelves, altering ocean currents and creating new pathways for the global conveyor belt. These changes in turn affect how heat and carbon are distributed, reinforcing the climate trajectory set by eccentricity. During interglacials, meltwater returns to the sea, raising sea levels and submerging coastal plains. The ocean basin geometry changes modestly, shifting circulation once again. This slow dance of currents, temperature, carbon, and sea levels becomes one of the most important mechanisms linking orbital cycles to global climate. Eccentricity does not act alone. It whispers a small change in sunlight distribution. Ice sheets respond, oceans amplify, the atmosphere shifts, and through it all, the deep ocean records every phase, every transition, every breath. If you could stand on the seafloor 3,000 meters down, darkness pressing in, cold currents brushing past, you would not feel time. You would not know that the water drifting beside you carries the memory of a world that existed before your species learned to shape tools. But in the chemistry of those waters, in the shells of tiny foraminifera resting in the sediment, in the isotopes deposited layer by layer, the story of eccentricity lives on. The ocean remembers everything, and it remembers on timescales far longer than ice, wind, or even stone. It remembers each cold breath of the planet, each warm exhalation, each subtle shift in Earth's ancient orbit. Dust is one of the quietest forces on Earth, light as breath, ancient as mountains, drifting across continents in tan veils that settle on oceans, ice sheets, and deserts. Yet when eccentricity stretches Earth's orbit and tilts the balance of sunlight, dust becomes something far greater, a climate amplifier. It cools the world, fertilizes waters, drives feedback loops, and marks the darkest moments of glacial cycles. In the long 100,000-year rhythm, dust rises and falls in perfect synchrony with the pacing of eccentricity, revealing a world where shade and powder work together to shape the fate of ice. Tonight, we step into this strange realm of airborne deserts, dust, darkness, and feedback, and watch how eccentricity magnifies all three into one of the planet's most powerful climate mechanisms. The first thing to understand is that dust is not random. It follows patterns etched by orbital cycles. During glacial expansions, as eccentricity suppresses northern summer sunlight and ice begins to grow, the world becomes drier. Cold air cannot hold moisture, rainfalls weaken, monsoons retreat. The subtropics shift into drought, forests shrink into patches, grasslands wither. As the land dries and vegetation retreats, loose sediments, long buried beneath soil or held in place by roots, become exposed to the wind. The Sahara, Arabian Peninsula, Central Asia, and the American West all transform into enormous dust-producing regions. This rise in dust is recorded in every major climate archive. Greenland ice cores contain thick layers of dark particles deposited during the coldest phases of glacial cycles. Antarctic ice shows similar patterns, with the highest dust levels occurring precisely when eccentricity reduced northern insulation. Loess deposits in China, vast blankets of windblown silt tens of meters thick, built up layer by layer during glacial times, each layer marking a pulse of dust rising from the deserts of Central Asia. Even marine sediments off northwest Africa show enormous increases in dust input during periods of weak northern summer sunlight. The timing is too consistent to ignore. Dust cools the planet through several mechanisms, beginning with sunlight reflection. When vast amounts of dust enter the atmosphere, they scatter incoming solar radiation, reducing the amount of heat reaching Earth's surface. The effect is subtle when seen day by day, but across centuries, it deepens global cooling. During glacial maxima, atmospheric dust concentrations were up to 20 times higher than today. This thick haze reflected enough sunlight to reinforce the cold conditions triggered by eccentricity. But dust's influence goes far beyond simply blocking sunlight. The second major effect lies in its ability to fertilize the oceans. Iron is a micronutrient essential for phytoplankton growth, and many parts of the world's oceans, especially the Southern Ocean, are iron-limited. When dust storms sweep iron-rich particles across the sea, they spark enormous plankton blooms. These microscopic plants draw carbon dioxide from the atmosphere during photosynthesis. When they die, much of this carbon sinks into the deep ocean, where it remains stored for thousands of years. This biological pump, enhanced by dust, significantly lowers atmospheric CO2 during glacial periods. Ice core records show that CO2 concentrations fall by 20–30% during these times, not solely because of eccentricity's cooling, but because dust-fed plankton remove carbon from the air. This reduction in CO2 reinforces the global cooling trend, further lowering temperatures and helping ice sheets expand. Once again, a small orbital shift cascades into a major climate transformation through long, interconnected feedback loops. The third major dust mechanism involves surface albedo, the reflectivity of Earth. When dust settles on snow or ice, it can either darken the surface, reducing reflectivity, or, in some cases, increase it depending on the mineral composition. But over large land surfaces, dust accumulation tends to brighten the landscape, especially when deposited on dry soils or lightly colored sands. This increased reflectivity contributes to additional cooling. Vast regions of Australia, Central Asia, and North America experience this effect during glacial times. The combination of dust-covered landscapes and weaker summer sunlight ensured that the northern continents became colder still, allowing ice sheets to continue growing. Eccentricity amplifies all these dust-related processes. When Earth's orbit stretches significantly, northern summers weaken. Weak summers mean less snowmelt. Less snowmelt means more ice. More ice means colder winds. Colder winds mean drier continents. Drier continents mean more dust. More dust means cooler oceans and lower CO2. Lower CO2 means deeper cooling. The cycle loops and intensifies. Dust becomes one of eccentricity's strongest accomplices. But dust also affects regional climates in dramatic ways. In North Africa, during high eccentricity phases when monsoons weaken, the Sahara expands into a massive dust source. Models and sediment records suggest that during some glacial maxima, the Sahara produced more dust than all modern deserts combined. This dust blew westward across the Atlantic, settling in the Caribbean and fertilizing the Amazon rainforest. Incredibly, the lush Amazon ecosystems we admire today owe part of their ancient vitality to dust storms born from an eccentricity-driven climate thousands of years ago. In Asia, the retreat of vegetation along the Tibetan Plateau and Gobi Desert exposed enormous regions of silt. Winds sweeping across these plains carried dust into eastern China, forming the immense Loess Plateau. Some of these Loess layers correspond exactly with eccentricity maxima, each layer marking a moment when weak summers and strong winds combine to reshape landscapes across half a continent. Antarctica also reveals the influence of dust. Although far from major deserts, it receives dust from Patagonian sources during glacial periods. Ice cores drilled at Dome Sea and Vostok show distinct layers of dust corresponding to the coldest phases of each 100,000-year cycle. The rise and fall of dust aligns precisely with eccentricity-driven insulation changes. When eccentricity decreased and summers strengthened, ice melted, continents moistened, vegetation returned, and dust levels dropped. One of the most fascinating aspects of dust feedback lies in how abruptly it changes during deglaciation. As eccentricity decreases and northern summers begin aligning with perihelion, warming accelerates. Ice sheets melt, sea level rises, rainfall increases, deserts shrink, vegetation spreads, dust production collapses. Within a few thousand years, global dust levels drop by orders of magnitude. This sudden decline in dust reduces ocean fertilization, allowing atmospheric CO2 to rise again. Rising CO2 amplifies warming, completing the transition from glacial to interglacial. This abrupt transition is visible in every climate archive. Antarctic ice cores show dust levels plummeting as CO2 rises. Marine sediments show reduced iron deposition. Low S accumulation slows dramatically. Paleolake sediments record sudden shifts from dusty to wet conditions. This rapid switch marks the moment when eccentricity's grip loosens and Earth exhales warmth. Even today, the fingerprints of ancient dust remain. Coral reefs across the Caribbean contain layered traces of Saharan dust deposited during glacial periods. The soils of the American Midwest, now among the most fertile in the world, are built from wind-blown glacial dust. The nutrient cycles of the Amazon rainforest still rely on Saharan dust carried by the trade winds, a long-distance memory of orbital cycles that shaped ecosystems thousands of years ago. Dust, darkness, and feedback loops form a triad that helps translate eccentricity's subtle orbital changes into full-blown climate transformations. Dust dims the planet, fertilizes oceans, lowers CO2, and reinforces cold. When dust falls, warmth returns. And all of it, this rise and fall of airborne deserts, begins with the slow stretching of Earth's orbit, a gentle shift that makes summers weaker, winters harsher, continents drier, and the sky itself heavier with the memory of ancient winds. Rain is not a constant across Earth. It wanders. It drifts north and south, swells and collapses, expands into lush belts, or shrinks into narrow ribbons, depending on how the world tilts and how sunlight is delivered. And when eccentricity stretches Earth's orbit, altering the contrast between seasons, the wandering becomes dramatic. Monsoons that once flooded entire regions weaken into brittle showers. Tropical rain belts that nourished forests collapse into bare ground. Deserts advance. Lakes vanish. All the while, eccentricity's slow modulation of sunlight decides where rain belongs and where it does not. Tonight, we follow that drifting rain, beginning in the deep tropics and watching how eccentricity reshapes entire continents every 100,000 years. The key to understanding tropical rainfall lies in the Intertropical Convergence Zone, or ITCZ, a narrow, powerful belt of rising air and thunderstorms circling the globe. The ITCZ migrates northward and southward each year as the sun shifts overhead. But its movements are not symmetric. It always favors the warmer hemisphere. The warmer the land and ocean on one side of the equator, the farther the ITCZ drifts into that hemisphere. During times when eccentricity amplifies seasonal contrasts, this migration becomes more extreme. When northern summers weaken due to aphelion alignment, tropical heat shifts southward, dragging the ITCZ along with it. Rain deserts the north, monsoons falter. The Hadley cell, the great atmospheric circulation loop, tilts. This single shift becomes the architect of continental-scale climate transformation. Consider Africa. During high eccentricity phases, when precession weakens northern summer insolation, Africa's northern hemisphere receives less heating. The ITCZ stays far south. The West African monsoon weakens, and the Sahel, once humid and green, dries dramatically. Dust storms swell. Lake Megachad, once larger than the Caspian Sea, shrinks or vanishes completely. The White Nile slows. Archaeological evidence shows that early human groups living along now deserted regions depended heavily on these rainfall shifts. Whenever eccentricity suppressed northern rains, populations retreated southward. When eccentricity reversed and monsoons strengthened, they returned to colonize newly fertile land. Asia experiences similar chaos. The Asian monsoon, one of the strongest climate systems on Earth, depends on the intense heating of the Tibetan Plateau during northern summer. When eccentricity weakens these summers, the plateau warms less, producing weaker thermal contrasts between land and sea. The monsoon collapses, rainfall decreases across India, China, and Southeast Asia. Dust from the Taklamakan and Gobi deserts intensifies. Pollen records from Chinese cave deposits show clear transitions. During strong monsoons, forests expand, but during eccentricity-suppressed summers, steppe and desert plants take over. Marine sediment cores from the Arabian Sea reveal rhythmic changes in upwelling intensity linked perfectly to monsoon strength. During high eccentricity phases when northern summer rainfall weakens, marine productivity drops in the Arabian Sea. The ocean surface becomes nutrient-poor. Dust storms from Arabia and northeast Africa surge. The pattern reverses when eccentricity strengthens northern summers. Monsoons roar back, lakes refill across Arabia, ancient rivers flow again, and the Green Arabia era returns, an interval when hippos, crocodiles, and human groups lived in what is now one of the driest deserts on Earth. South America responds in equally dramatic fashion. The South American monsoon system, which feeds the Amazon basin with enormous amounts of rainfall, follows the heat contrast between hemispheres. When eccentricity weakens northern summers, heat shifts southward, intensifying rainfall over central and southern Amazonia, while drying the northern Amazon and the Caribbean. Ancient lake sediments in Brazil show wet phases aligning with eccentricity maxima, while regions farther north exhibit dustier and drier conditions. This push and pull of moisture shaped the very formation of Amazonian ecosystems, periodically expanding rainforests, then carving open savannas, then closing them again as orbital cycles shifted. The tropical Pacific also participates in this dance. Eccentricity-induced changes in seasonal contrast can modulate ENSO, the El Niño Southern Oscillation, by influencing the strength of trade winds and the distribution of warm surface waters. During weak northern summers, trade winds often strengthen, enhancing upwelling along South America's Pacific coast and cooling the region. This cooling propagates across the equatorial Pacific, affecting rainfall patterns globally. Coral records from the Central Pacific show ancient periods of stronger La Niña-like conditions coinciding with high eccentricity. These episodes likely intensified monsoon failures in Asia and droughts across northern Africa. The Western Hemisphere. Warm Pool, an area of warm water in the Caribbean and tropical Atlantic, also responds to eccentricity-controlled sunlight. When northern summer weakens, the warm pool cools slightly and shrinks. This reduces moisture transport into Central America and the southern United States. Ancient cave formations in Belize record dry intervals that match perfectly with eccentricity maxima, each period showing reduced stalagmite growth due to lower rainfall. Across the Indian Ocean, the story repeats. The Australian monsoon depends on southern summer heating. During high eccentricity phases, when southern summers become shorter and more intense at perihelion, the Australian monsoon strengthens dramatically. Northern Australia floods, lakes fill, ancient shorelines appear and vanish in repeating cycles. Sediment cores from lake air show alternating wet and dry phases that map directly to eccentricity-modulated rainfall. Even the remote islands of the South Pacific preserve this rhythm. Pollen from New Caledonia, Samoa, and Vanuatu reveals repeated expansions of wet forest, followed by contractions into drier scrubland, each cycle matching orbital-driven rainfall shifts. One of the most powerful examples of eccentricity reshaping rainfall lies in the megalakes of Africa's Rift Valley. Lake Turkana, Lake Victoria, Lake Tanganyika, and Lake Malawi, all of them rose and fell dramatically over the last million years. Sediments in these basins reveal lake levels climbing during strong monsoons and collapsing during weak ones. These expansions and contractions often align with eccentricity maxima, when northern summer sunlight dipped low, weakening the monsoon and drying entire regions. During each humid interval, new ecosystems flourished. During each dry interval, they retreated. Eccentricity-modulated rainfall also influences fire cycles. During weak monsoons, vegetation becomes sparse and dry, fueling widespread wildfires. Charcoal layers in African and Australian sediments record massive fire events during eccentricity maxima. Conversely, during strong monsoons, rain suppresses fires, forests expand, and charcoal deposition drops sharply. The rise and fall of fire shapes ecosystems, favoring fire-adapted plants during dry phases and broadleaf forests during wet phases. But perhaps the most striking consequence is how rainfall patterns sculpted early human migrations. When eccentricity pushed the ITCZ southward and weakened African monsoons, the Sahara expanded. Human groups retreated into wetter refuges, river valleys, coastal zones, and mountain highlands. When eccentricity later strengthened northern summers and monsoons returned, the Sahara transformed into savanna, crisscrossed by rivers and dotted with lakes. This opened migration corridors across North Africa, enabling human dispersal across the continent and into Eurasia. These green Sahara windows appear repeatedly in the archaeological record. Each window aligns with orbital cycles. Rainfall shapes survival. It shapes food webs, predator ranges, lake fisheries, grazing migration, plant foraging zones. When rain deserts a region, people leave. When it returns, they follow it back. And eccentricity, quietly stretching Earth's orbit, decides when these windows open and close. As this section softens into its final breaths, imagine rain moving like a living ribbon across the world. Some eras bring it north, feeding forests in Europe and lakes in the Sahara. Other eras shift it south, flooding Amazonia while drying Asia. The rain wanders. The continents breathe with it. And beneath everything, beneath jungles, deserts, and ancient lake beds, eccentricity guides where the storms go, where the rivers flow, and where life gathers in each long turning of Earth's orbital path. If you could fly over Africa, North America, or Central Asia during one of Earth's ancient high eccentricity phases, you would see something extraordinary. Vast inland seas, shimmering under the sun, sprawling across regions that are deserts today. These were the world's megalakes, colossal bodies of water that appeared and vanished in rhythm with Earth's orbit. Their shorelines rose hundreds of meters during wet phases and collapsed into cracked clay pans during dry ones. And through all their dramatic transformations, eccentricity quietly choreographed the entire performance. Tonight, we follow these ancient waters, how eccentricity filled them, how it drained them, and how their pulse became one of the clearest fingerprints of the 100,000-year cycle. Megalakes form when rainfall patterns shift dramatically, and as we saw in the previous section, rainfall depends on where sunlight warms the land most intensely. During phases when eccentricity strengthens northern summers, especially when perihelion aligns with the northern hemisphere, the land heats more strongly, intensifying monsoon circulation. Rains become abundant, rivers swell, basins fill, lakes spread across continents. But when eccentricity suppresses northern summers and precession pushes the ITCZ southward, these lakes shrink or vanish entirely. What remains are thick layers of salt, desiccated shorelines, ancient beaches perched high above modern plains, and a story of orbital pacing written in mud, sand, and stone. One of the most dramatic examples is Lake Megachad in Central Africa. At its peak during strong monsoon periods linked to eccentricity minima and intense northern summers, Megachad covered more than 350,000 square kilometers, larger than today's Caspian Sea. Its waters stretched across modern Chad, Niger, Nigeria, and Cameroon. Satellite radar mapping has revealed ancient shorelines hundreds of kilometers apart, showing that the lake rose and fell in enormous swings every time the monsoon strengthened or collapsed. These transitions align almost perfectly with eccentricity-driven changes in northern hemisphere insolation. When eccentricity cycles shifted, monsoons weakened, and the lake contracted into the much smaller Lake Chad we know now, a fragile remnant of its majestic past. The East African Rift Valley, stretching from Ethiopia down through Kenya, Tanzania, and Malawi, holds even more striking stories. Lake Victoria, Lake Turkana, Lake Tanganyika, and Lake Malawi all preserve ancient shorelines and sediment layers, showing massive expansions during strong monsoon periods. Some of these lakes rose more than 100 meters, flooding entire basins, connecting waterways, and creating immense habitats for fish, crocodiles, hippos, and early human populations. During dry, high eccentricity phases, the same lakes shrank dramatically, leaving behind dusty plains and exposed riverbeds. Lake Turkana, for example, has oscillated between a vast freshwater lake and a shallow saline body dozens of times over the past million years. The timing of each major highstand aligns squarely with insolation peaks tied to orbital eccentricity. Lake Malawi offers perhaps the clearest, deepest record of this pattern. Its sediment core stretches back more than 1.2 million years, and its layers alternate between wet-phase organic sediments and dry-phase sands. These cycles follow the 100,000-year rhythm precisely. When eccentricity suppressed northern summer sunlight, the African monsoon weakened, the lake level dropped drastically, and dust deposition increased. When eccentricity reversed and summers strengthened, rainfall surged and the lake filled. This lake is among the world's strongest natural tape recorders of eccentricity's climate control. But Africa was not alone in this watery transformation. The Sahara itself, now the planet's largest hot desert, once hosted a constellation of megalakes interconnected by seasonal rivers. During strong northern summer monsoons, periods known as the African humid periods, the Sahara blossomed with vegetation, rivers flowed across its plains, and lakes the size of small seas filled its depressions. Evidence of these ancient water bodies remains in the form of fossilized fish skeletons, crocodile remains, and human settlements found far from any modern water source. Every humid period corresponds to an eccentricity configuration that strengthened northern summer sunlight, drawing the ITCZ northward and allowing rain to wash across the desert. North America tells a similar story, but on an even grander scale. During and after the last glacial maximum, eccentricity began to relax, precession strengthened northern summer sunlight, and massive meltwater from the Laurentide ice sheet flowed into great basins across the continent. The result was Lake Agassiz, an enormous inland sea larger than all of today's Great Lakes combined. At its height, Lake Agassiz covered nearly half of modern Canada's prairie provinces. Its periodic drainage events, some catastrophic, reshaped ocean circulation, altered global climate, and left shorelines visible from space. The formation, expansion, and eventual emptying of Lake Agassiz all followed the timing of orbital cycles. When northern summers warmed quickly, meltwater surged into the basin. When summers weakened again, freezing slowed the inflow. It was a liquid mirror reflecting eccentricity's rhythm in North America's heart. Further west, Lake Bonneville once covered much of what is now Utah, an inland sea 10 times larger than modern Great Salt Lake. Around 18,000 to 15,000 years ago, it reached depths of more than 300 meters as climate warmed during a phase of increasing northern summer insolation. Its sudden outflow, known as the Bonneville Flood, carved enormous canyons and reshaped the Snake River plain. But just a few thousand years earlier, the basin had been in a near-dry phase, its waters dramatically lower, due to weakened northern summers tied to eccentricity. This rise and fall left behind the Bonneville salt flats, wave-cut terraces, and sediment layers that map precisely onto orbital cycles. In Central Asia, paleolake systems such as Lake Lop Nur and Lake Balkhash also record eccentricity-driven hydrological change. Low S deposits, ancient river channels, and shoreline fluctuations show repeated wet and dry phases mirroring the long cycles of insolation. The Tibetan Plateau, acting as a high-altitude climate engine, intensified monsoonal rains during periods of strong northern summer sunlight. Lake levels rose across northern China and Mongolia, supporting herds of megafauna and early nomadic communities. When eccentricity weakened the monsoon, these lakes shrank or vanished, forcing hunter-gatherers to migrate toward the coasts or into mountain refuges. South America likewise bears the scars of ancient megalakes. The Altiplano of Bolivia and Peru once held Lake Tauca, a vast water body that filled the region's salt flats during strong southern monsoons. Sediment cores from these basins show repeated highstands coinciding with eccentricity phases that intensified southern hemisphere summer heating. These wet phases supported thriving ecosystems, human settlements, and migratory routes across what is now one of the driest regions on Earth. When eccentricity shifted and rainfall weakened, Lake Tauca evaporated, leaving behind vast salt flats such as Salar de Uyuni, the world's largest. Even Australia joined this global rhythm. Lake Eyre, the continent's largest drainage basin, cycled between shallow saline pools and vast freshwater expanses depending on monsoon intensity. During high eccentricity phases when the southern summer aligned with perihelion, the Australian monsoon strengthened, filling Lake Eyre and supporting biodiversity across the inland desert. Aboriginal archaeological records reveal human occupation during these wet phases and abandonment during the dry ones. These lake cycles were not gentle rises and falls. They were dramatic, world-shaping transformations. Lakes became seas, seas became dust bowls, animals flourished, then retreated. Humans followed the water, hunting along shorelines in wet phases and leaving entire basins during drought. Megalakes, then, are more than geological curiosities. They are the clearest expression of how eccentricity reshapes continents. When orbital geometry strengthens summer sunlight, lakes bloom into existence. When eccentricity pulls sunlight away, they vanish. And through each cycle, shorelines move like slow tides across the land, marking Earth's long heartbeat. As this section settles, imagine standing on a high plateau, looking out over a great shimmering lake. Then imagine returning 20,000 years later to find nothing but cracked earth stretching to the horizon. The water has gone, carried away not by rivers, but by the quiet turning of Earth's orbit, a reminder that oceans, rain, and lakes all follow the deep pulse of eccentricity. Life does not evolve in a vacuum. It evolves inside climate rhythms, and few rhythms have shaped life on Earth more profoundly than the long pulse of eccentricity, the 100,000-year rising and falling of ice, rain, temperature, and habitat that forces species to move, adapt, shrink, expand, or vanish. Every creature alive today carries somewhere in its biology the imprint of these cycles. Grasslands advanced and retreated, forests opened, closed, and opened again, rivers carved new paths, deserts shifted like wandering giants. And each of these environmental swings acted as a selective pressure, pushing species toward traits that helped them cope with a world that never stayed still. Tonight, we step into this evolutionary landscape and watch how eccentricity, quiet, celestial, and patient, became one of the greatest sculptors of life itself. To understand how species respond to eccentricity-driven climate shifts, imagine a world that transforms slowly but relentlessly. Every 100,000 years, northern hemisphere summers weaken, ice sheets expand, and global temperatures fall. Grasslands spread across continents, forests shrink. Many species migrate southward in search of warmth and food. Then, suddenly, over just a few thousand years, eccentricity reverses, precession switches, hemispheric heating, summers strengthen, ice collapses, and forests surge back into northern latitudes. Species are forced to migrate again, adapt again, or perish. Over millions of years and dozens of cycles, this repeated squeeze and release becomes a powerful evolutionary engine. In Africa, the birthplace of humanity, the effects were profound. During strong monsoon phases tied to eccentricity minima, East Africa blossomed with lakes, rivers, wetlands, and forests. During weak monsoon phases tied to eccentricity maxima, these same landscapes dried into grasslands and dust-filled plains. Fossil pollen from the Rift Valley shows that forest ecosystems shrank dramatically during dry phases, replaced by savanna and steppe vegetation. Large herbivores, zebra, buffalo, gazelle, antelope, expanded during these open phases. Predators such as lions, hyenas, and early hominins adapted to open habitat hunting and scavenging. This pulsing environment selected for mobility, endurance, and flexibility. A species that could not move with the shifting rain belts faced starvation and extinction. Those that could, those that evolved long limbs, efficient cooling systems, migratory behaviors, and dietary flexibility, survived. Grassland specialists flourished during eccentricity-driven dry periods. The iconic African megafauna, elephants, zebras, wildebeest, rhinos, trace their diversification to periods when eccentricity repeatedly dried the continent. Each 100,000-year shift acted as a reset button, forcing species to recolonize old habitats or carve new ecological niches. Fossil evidence shows waves of herbivore expansion during wet phases and contraction during dry phases, all aligned with orbital cycles. In Eurasia, megafauna evolved extraordinary cold adaptations during repeated glacial cycles. Mammoths grew thick fur, massive fat reserves, and curved tusks ideal for sweeping snow from grass. Woolly rhinoceroses developed dense coats and wide bodies for heat retention. Steppe bison, musk oxen, and reindeer adapted to nutrient-poor grasses and bitter glacial winds. Their distribution maps, based on bones found across Siberia, Mongolia, and northern Europe, show clear pulses tied to eccentricity, expanding across continents during cold periods and retreating into refuges during warm ones. Even birds evolved in response to these cycles. Many migratory species first developed long-distance flight patterns during glacial periods when food scarcity forced them to chase seasonal resources across continents. Eccentricity's influence on rainfall, monsoons, and temperature created irregular resource distributions that rewarded mobility. The very idea of seasonal migration, millions of birds sweeping north and south each year, has its roots in the orbital rhythms that reshaped landscapes again and again. In the oceans, eccentricity's power was equally transformative. Glacial periods increased nutrient delivery from dust and exposed shelf regions, enhancing marine productivity. Plankton blooms surged during glacial maxima, supporting vast populations of fish, whales, and marine mammals. During interglacial periods, nutrient levels dropped as dust weakened and sea levels rose, submerging nutrient-rich shelves. Ocean ecosystems reorganized. Species adapted to colder, nutrient-rich waters thrived during glacial phases but declined sharply during warm ones. Whale migration routes, fish population cycles, and even coral reef growth patterns all bear the imprint of eccentricity's climate regulation. Yet no species felt eccentricity's pressure more intimately than early humans and their ancestors. Hominins evolved in landscapes constantly shifting between forests and grasslands. Each cycle forced them to innovate, new tools, new hunting strategies, new diets, new social behaviors. The growth and retreat of megalakes created repeated opportunities for freshwater resources, fish, birds, and shoreline foraging, followed by periods of aridity that pushed early humans toward broader diets and cooperation. Studies of Homo erectus fossils show that they spread beyond Africa during eccentricity-driven humid phases when green corridors opened across the Sahara and Arabian Peninsula. Later, Homo heidelbergensis and Neanderthals expanded into Europe during glacial periods, adapting to cold climates with broad torsos, shorter limbs, and specialized hunting strategies. Their disappearance, too, aligns with major eccentricity phases that reshaped Europe's ecosystems. Modern Homo sapiens emerged during a time of dramatic climate fluctuation. Genetic evidence suggests that early human populations repeatedly contracted into small refuges during dry phases, especially in southern Africa, and then expanded during wet phases driven by stronger monsoons. Each expansion introduced new genetic mixing, new migrations, and new cultural innovations. The archaeological record shows sudden bursts of creativity, symbolic art, advanced tools, long-distance trade, emerging during periods when eccentricity strengthened rainfall, created stable wetlands, and increased resource availability. Even human cognition may have been shaped by climate pulses. A world that changes slowly but relentlessly rewards behavioral flexibility, long-term planning, and cooperation. The species that survived were those that could foresee scarcity, store food, share knowledge, and adapt to new environments. Eccentricity did not just shape where humans lived, it helped shape who humans became. Beyond hominins, eccentricity influenced countless other evolutionary trajectories. Amphibians expanded during wet phases and retreated during dry ones. Reptiles in Africa and Asia experienced pulses of diversification tied to shifting desert belts. Birds adapted to moving grassland-forest boundaries. Fish in megalakes evolved rapidly in isolated basins that repeatedly filled and drained. Some lakes even produced species flocks, groups of many closely related species evolving in parallel. because eccentricity cycled habitats on timescales that promoted repeated isolation and reconnection. Insects, too, followed these rhythms. Grasshoppers, locusts, and beetles expanded explosively during dry phases when grasslands surged. Mosquito populations shifted with the rise and fall of wetland habitats. Pollinators followed flowering plants as they moved with shifting rainfall zones. Eccentricity created a world of constant motion, but the motion was slow and vast, measured in tens of millennia. It gave species time to adapt, evolve, or migrate, but not enough time to remain unchanged. Every cycle demanded response. One of the most fascinating evolutionary outcomes lies in refugia, regions that remained stable through both glacial and interglacial phases. These refugia became reservoirs of genetic diversity. In Europe, southern peninsulas such as Spain, Italy, and the Balkans sheltered species during glacial maxima. In Africa, the Ethiopian highlands, coastal Kenya, and the Congo basin served as safe havens. These regions ensured life survived upheavals, only to recolonize entire continents when climate warmed again. The pattern appears in the DNA of modern plants, animals, and humans. As eccentricity guided the climate, life adjusted its pace. Each 100-year breath of cold and warmth acted like a slow evolutionary metronome, setting the tempo of adaptation. And as this section eases into silence, imagine the world not as static landscapes, but as shifting canvases, forests advancing and retreating like tides, animals migrating along ancient corridors, early humans tracking water and shade, and species everywhere trying to keep pace with a planet that, driven by its orbit, refuses to stand still. If you traced every ancient footstep in human history, every migration, every dispersal, every long journey into unknown lands, you would eventually discover that many of them follow a single hidden pattern: the slow turning of Earth's orbit. Eccentricity did not simply shift climates or sculpt ecosystems. It opened and closed migration corridors, dried and refilled crossing routes, lifted and drowned coastlines, and changed entire continental outlines. Humans did not move randomly across the Earth. They moved in rhythm with eccentricity's 100,000-year cycle, guided first by water, then by grassland, then by cold, then by warmth, each phase creating windows of opportunity or walls of ice that shaped where our ancestors could and could not go. Tonight, we follow those ancient paths across deserts, seas, and glaciers to see how eccentricity's long pulse helped steer the great human odyssey. The earliest hints of this connection appear in Africa, where the story of our species began. The African humid periods, intervals when the Sahara transformed into grassland, full of rivers, lakes, and thousands of animals, appear in near-perfect synchronicity with eccentricity minima, when northern summer sunlight strengthened and monsoons surged northward. During these wet phases, ancient lakes spread across the Sahara, forming fertile corridors that allowed Homo sapiens and earlier species such as Homo heidelbergensis to explore lands that are now barren. Archaeological sites in what is today one of the driest deserts in the world contain tools, hearths, and even fish remains left behind by small bands of early humans who followed shifting rivers and wetlands across northern Africa. These were not random wanderers. They moved because eccentricity strengthened the monsoon, drawing rainfall north and creating a green portal out of Africa. Genetic evidence supports this. Major expansions in human population size correspond with these wet phases when resources were abundant and travel routes opened. Then, when eccentricity reversed, summers weakened, monsoons collapsed, and the Sahara dried. Migration corridors closed, populations retreated to more stable refuges, the Nile Valley, East African highlands, and coastal zones, waiting for the next orbital window to open. The timing of the first major out-of-Africa dispersal, around 120,000 to 90,000 years ago, aligns beautifully with one of these windows. During a period of strong northern summer insolation, the Sahara was green and Arabia was humid, filled with lakes and grasslands. This created the Arabian Green Corridor, a lush pathway that connected Africa to the Arabian Peninsula and onward into Eurasia. Fossil sites in Saudi Arabia, such as Al-Wusta and Jubba, contain hippo bones, freshwater mollusks, and human tools from this phase, proving that early Homo sapiens crossed Arabia during wet intervals driven by orbital forcing. But when eccentricity shifted again and monsoons weakened, Arabia dried into desert once more, trapping populations in Eurasia and cutting off the connection to Africa. Genetic signatures of these isolated groups remain in modern humans, evidence of how orbital cycles shape the branching of our species. Later migrations followed similar rhythms. Around 70,000 years ago, another major eccentricity minimum strengthened northern summer sunlight again. The monsoon expanded, the Sahara briefly softened. Sea levels, still suppressed by large ice sheets, were low, exposing broad land bridges along the coastlines. This combination, green Africa, humid Arabia, lowered sea levels, allowed a second, far more successful wave of Homo sapiens to leave Africa. This wave eventually replaced or absorbed earlier dispersals and gave rise to all non-African populations alive today. Eccentricity also shaped the paths humans took through Eurasia. During glacial maxima, huge ice sheets blocked northern routes, forcing humans southward. But during intermediate warm phases, especially those tied to rising eccentricity and stronger summers, grasslands opened across the Middle East, Iran, and Central Asia. These Pleistocene steppe highways allowed human groups to travel eastward toward India, Southeast Asia, and eventually China. Archaeological layers in the Levant show repeated cycles of occupation and abandonment, corresponding to these environmental shifts. In Europe, eccentricity cycles determined when early humans could push into high latitudes. During warm intervals, forests spread across Europe, supporting diverse fauna. Neanderthals thrived in these wooded landscapes. But during eccentricity-driven glacial advances, Europe transformed into tundra and steppe. Neanderthal populations retreated into southern refuges, the Iberian Peninsula, Italy, the Balkans. Modern Homo sapiens entered Europe during one of these warmer periods, around 45,000 years ago, when eccentricity weakened glacial advance and ecosystems temporarily softened. Soon after, eccentricity shifted and climate became unstable. Some researchers believe this climate volatility contributed to the Neanderthal decline, as warming and cooling swings disrupted their specialized hunting strategies. Meanwhile, Homo sapiens, with more flexible diets and broader networks, adapted. In Siberia, eccentricity-controlled climate pulses opened and closed migration routes repeatedly. During cold phases, grasslands expanded across the mammoth steppe, creating rich hunting grounds. Humans followed herds of bison, mammoths, and reindeer across the vast plain. During warmer, wetter intervals, forests advanced, reducing grazing land and pushing human groups south or east into refuges. These cycles left archaeological fingerprints at sites like Denisova Cave, where layers show alternating phases of human presence linked to glacial and interglacial environments. The movement into Australia also aligns with eccentricity. Around 65,000 years ago, during an interval of lower sea levels and shifting rainfall belts, land bridges connected Australia, New Guinea, and Tasmania into one supercontinent, Sahul. Monsoon systems intensified in the north due to eccentricity-modulated southern hemisphere summers, providing the rainfall necessary for human groups to cross coastal regions and follow rivers inland. Rising eccentricity and warming later reversed these conditions, raising sea levels and isolating populations across the Australian continent. Perhaps the most dramatic migration event shaped by orbital cycles was the crossing into the Americas. For tens of thousands of years, humans could not enter the Americas because the Laurentide and Cordilleran ice sheets merged, forming an impassable wall. But eccentricity eventually shifted, strengthening northern summer sunlight and pushing the planet into rapid deglaciation around 16,000 years ago. Ice sheets retreated. Coastal routes opened along the Pacific. The Bering Land Bridge, exposed during glacial low sea levels, remained walkable. Human groups crossed into a new world. Climatic windows created by eccentricity also determined when and where humans could thrive once they arrived. The opening of ice-free corridors around 14,000 years ago allowed populations to expand south into the heart of the Americas. New lakes, rivers, and grasslands formed as climate warmed quickly. The archaeological record, from Monteverde in Chile to Clovis in North America, reveals a burst of human activity during this eccentricity-aligned warming. But eccentricity didn't just guide large-scale migrations, it shaped how early human groups moved seasonally. During wet phases, nomadic groups ranged widely across savannas and wetlands. During dry phases, they contracted into refuges, developing more complex tool traditions, symbolic art, and social structures as resources became scarce. The rise and fall of rainfall belts, lakes, and forests created evolutionary pressure for flexibility. Humans learned to exploit varied environments, coastlines during wet phases, inland plains during dry ones. They learned to anticipate environmental change from generation to generation. Deep time taught adaptability. This long orbital choreography culminated in a profound truth. Humans migrated not in spite of Earth's changing orbit, but because of it. Eccentricity created the pathways, closed the doors, shaped the opportunities, and sculpted the challenges. Our species learned to move with the planet's breath. As this section fades, imagine ancient humans standing on a green Sahara plain, watching birds migrate north with rains. Imagine others walking along the newly exposed coast of Beringia, kelp forests shimmering beneath them. They did not know the sky above was shifting their destiny, but they walked forward anyway, step by step, in rhythm with a planet whose orbit quietly guided the course of human history. Civilizations rise from stable ground, stable rivers, stable rains, stable seasons, stable temperatures. Yet behind every fertile valley, every ancient city, and every cradle of agriculture lies a climate shaped by tens of thousands of years of orbital cycles. Eccentricity, the quiet architect of glacial ages and monsoon rhythms, did not stop influencing humanity once our species began farming and building settlements. Instead, it continued to whisper into the climate, gently nudging rainfall belts, shifting deserts, altering the strength of monsoons, and occasionally destabilizing whole societies that relied on predictable weather. Tonight, we explore how early civilizations sensed, without knowing, Earth's long orbital pulse, and how eccentricity shaped the landscapes that allowed humanity to build its first cities. To understand this connection, we must return to the end of the last ice age, roughly 12,000 to 10,000 years ago. Earth was warming rapidly. This global thawing was triggered by eccentricity shifting the alignment of precession and strengthening northern summer sunlight. As the Laurentide and Eurasian ice sheets collapsed, sea levels surged more than 100 meters. Coastlines flooded, vast plains disappeared under rising seas. Freshwater poured into the oceans, reorganizing currents and altering rainfall patterns across the world. This was not a gentle transition, it was a planetary exhale. And in the wake of this exhalation, new landscapes emerged: stable rivers, fertile floodplains, widening grasslands, and warmer climates. These conditions became the foundation for agriculture. Civilizations did not arise at random moments. They emerged during the most stable climatic phase Earth had experienced in millions of years, the early Holocene. And that stability was the direct consequence of eccentricity dropping to an unusually low value about 10,000 years ago. When eccentricity is low, Earth's orbit becomes nearly circular. Seasonal contrasts soften, climate becomes more predictable. This is exactly what happened during the early Holocene, a period when eccentricity reached one of its lowest points of the last 400,000 years. Because summers no longer swung wildly in strength, rainfall patterns steadied, monsoons stabilized, river systems became reliable, forests regenerated, grasslands expanded. Human populations, long forced to migrate with shifting climates, found themselves in an environment that finally stayed put. The Fertile Crescent, birthplace of agriculture, blossomed precisely at this moment. The Tigris and Euphrates rivers, fed by snowmelt from the Taurus Mountains, became consistent sources of water. The annual flooding, neither too strong nor too weak, created predictable silt deposits ideal for farming. Archaeological evidence from sites like Jericho, Göbekli Tepe, Abu Huraira, and Çatalhöyük shows that plant cultivation began during a period of climate stabilization tied directly to falling eccentricity. Wheat, barley, lentils, and chickpeas flourished across landscapes no longer pulsating with severe rainfall shifts. But stability did not come suddenly. It grew gradually as orbital conditions softened extremes. During the previous glacial periods, eccentricity modulated massive swings in monsoons and temperature. But in the early Holocene, these swings diminished. The African humid period, when the Sahara turned green and countless lakes formed, coincided with a still relatively high obliquity and strong northern summers, amplified by mid-Holocene precession. Yet the underlying predictability of seasonal cycles came from low eccentricity, which kept the magnitude of climate extremes in check. This humid phase supported thriving pastoral and foraging communities across North Africa. Cattle, goats, and sheep spread across grasslands where modern travelers now see only dunes. Rock art in places like Tassili Najjar in Algeria depicts giraffes, elephants, and lush savannas, fauna and landscapes impossible today. These flourishing conditions lasted thousands of years because eccentricity's trough kept the climate gently stable. Then, as eccentricity began rising again several thousand years later, orbital conditions shifted. Precession gradually aligned northern hemisphere summers with aphelion, weakening monsoons. The Sahara dried. Lakes evaporated. Populations migrated toward the Nile, creating pressures that led to the early consolidation of settlements along the river. In this way, eccentricity indirectly contributed to Egypt's rise. The desertification of the Sahara-focused human populations into the Nile Valley, creating the density necessary for state formation. The same pattern unfolded across the Middle East. As monsoons weakened, rain-fed agriculture declined. Communities consolidated around perennial rivers, Tigris, Euphrates, Jordan. Irrigation emerged not as a cultural idea, but as a necessity in landscapes drying under changing orbital conditions. The world's earliest cities, Uruk, Eridu, Ubaid settlements, arose in these newly arid but river-rich environments shaped indirectly by eccentricity's modulation of monsoons. In the Indus Valley, one of the earliest urban civilizations emerged in a landscape profoundly shaped by orbital cycles. Around 8,000 to 6,000 years ago, the Indian monsoon was stronger due to high northern hemisphere summer insolation driven by precession. Rivers like the Ghaggar Hakra, often associated with the mythical Saraswati, flowed vigorously. Settlements flourished, but as eccentricity rose and monsoons weakened, these rivers dried. Indus cities like Mohenjo-Daro and Harappa responded by shifting populations eastward toward the Ganges basin, where monsoon rains remained more reliable. Their architectural patterns, reservoirs, drainage systems reflect a society shaped by water scarcity and a changing climate. China's early civilizations followed a similar arc. The Low S Plateau experienced alternating wet and dry periods controlled by eccentricity-modulated monsoon pulses. During strong northern summers, monsoons carried moisture deep into northern China, supporting millet agriculture. As insolation shifted, rainfall moved southward toward the Yangtze Basin, nurturing rice agriculture. Each phase corresponds to orbital cycles, inadvertently shaping where Chinese civilization would flourish. Mesoamerica and the Andes experienced eccentricity's influence too, though differently. In Mesoamerica, climate pulses influenced the expansion and contraction of tropical forests. The Maya civilization rose in part during a period of stable rainfall linked to lower eccentricity and favorable precessional alignment. When eccentricity climbed and rainfall variability increased, severe droughts struck around 800–1000 CE, contributing to societal stress and urban abandonment in the Maya lowlands. The same celestial mechanics that once stabilized their world now tested it. In the Andes, eccentricity influenced glacial extent, which in turn controlled water supply for high-altitude civilizations. Strong northern summers corresponded with rapid deglaciation, feeding rivers that supported agriculture along the Altiplano. When insolation patterns shifted, glaciers regrew or rainfall belts moved, challenging societies like Tiwanaku and the Wari Empire. Their rises and collapses match significant orbital phases. Across the world, eccentricity did not dictate human history, but it continuously reshaped the environmental stage upon which civilizations performed. Periods of low eccentricity fostered stability, predictable floods, steady monsoons, abundant crops, and the conditions necessary for early cities. Periods of rising eccentricity brought volatility, Drying deserts, shifting rain belts, collapsing lakes, forced migrations, and the birth of new societies and new refuges. One of the most profound consequences of this orbital influence was the emergence of cultural memory. Many civilizations preserved myths, rituals, and astronomical practices that reflect deep awareness, often symbolic, not scientific, of long-term climate rhythms. Flood myths in Mesopotamia, rainfall rituals in Mesoamerica, monsoon ceremonies in India, and sky-oriented temples in Egypt all echo the fundamental truth. Human survival depended on the rhythms of the sky. And though ancient people did not know eccentricity by name, they felt its imprint in every harvest and drought. They built calendars, they tracked the stars, they aligned their monuments to solstices and equinoxes. Their vigilance was a reflection of the subtle climate pressures shaped by orbital cycles. As this section softens, imagine early farmers watching the sky, noticing patterns that persisted for generations. Imagine priests marking solstice shadows in stone temples. Imagine traders following rivers born from melting glaciers. All the while, above them, Earth's orbit drifted gently, shaping a world stable enough for civilizations to rise and changeable enough for them to fall. The next turn of Earth's ellipse is already underway. Even as we speak, eccentricity is shifting, slowly, quietly, invisibly. And though modern humanity lives far removed from the glacial pulses that shaped our ancestors' world, we remain part of the same celestial system. The orbit continues to stretch and relax according to the same ancient rhythm, preparing the stage for climates our descendants will inherit tens of thousands of years from now. Tonight, in this final chapter, we rise from the deep past and step gently into the distant future, tracing what eccentricity's next cycle means for Earth, for climate, and for life on this planet. To begin, we must understand where Earth stands today within its orbital cycle. Right now, eccentricity is relatively low, about 0.0167, closer to a circle than at almost any point in the last several 100,000 years. It was similarly low, around 400,000 years ago, during a period known as marine isotope stage 11, one of the longest and warmest interglacials of the last million years. At low eccentricity, seasonal contrasts weaken, summers and winters soften, climate variability decreases. Ice sheets struggle to grow because northern summer sunlight remains consistently strong enough to melt winter snow. This low eccentricity state is part of the reason Earth entered the Holocene, a period of remarkable climate stability that allowed agriculture, cities, writing, and civilization itself to flourish. But eccentricity does not remain still. Over the next 50,000 years, Earth's orbit will gradually become more elliptical, peaking at a value around 0.03. That shift may seem small, but in planetary terms it is enormous. It means future seasons will once again diverge in intensity. The hemisphere aligned with perihelion will experience short, intense summers. The opposite hemisphere will endure long, weak ones. And that imbalance is the first whisper of future ice. Under natural conditions, if humans were not altering the atmosphere, Earth would likely begin trending toward glaciation roughly 50,000 to 60,000 years from now. Why? Because as eccentricity rises and precession shifts, northern summers would gradually weaken. Snow that melts today in Canada, Scandinavia, and Siberia would linger. Over thousands of years, that lingering would turn into accumulation. Accumulation into ice, ice into domes, domes into ice sheets. The planet would inhale again. But humanity has altered this rhythm in profound ways. Atmospheric CO2, which naturally oscillated between 180 and 280 parts per million over the last 800,000 years, now stands above 420 ppm. This level is unprecedented in human history and incompatible with ice sheet growth under conditions typical of past glacial inceptions. Even if eccentricity weakens northern summers in the distant future, elevated greenhouse gas levels would prevent the cold summers necessary for snow accumulation. Many climate models suggest that human influence has effectively postponed the next glaciation, possibly for hundreds of thousands of years. This does not break the eccentricity cycle. The orbit will continue to shift on schedule. Seasons will grow uneven. Rainfall belts will drift. The ITCZ will wander. Oceans will store and release heat. But the threshold for glacial inception, the delicate imbalance discussed earlier, may no longer be reachable for a long time. Humanity has raised that threshold. However, eccentricity will continue to influence climate even without triggering full ice ages. Rainfall patterns will follow its soft pulse. The African humid period, which last transformed the Sahara into grassland around 6 years ago, is expected to return not because of human warming alone, but because of precession's alignment with future orbital geometry. Around 10,000 to 12,000 years from now, northern summers will once again align with perihelion, strengthening monsoons in likely greening parts of the Sahara and Arabia. Eccentricity will be rising then, amplifying the effect. Similarly, monsoon systems across India, China, Australia, and South America will pulse with eccentricity's future cycles. Lake basins may refill, deserts may shrink, forests may expand in some centuries and retreat in others. Even without glaciation, Earth's climate will never be fixed. It will continue responding to the orbital choreography. Ocean circulation will shift too. Changes in seasonal contrast will alter patterns of deep water formation in the North Atlantic and Antarctic regions. The conveyor belt of global heat distribution will speed up or slow down accordingly. These shifts will interact with human-driven warming in ways not yet fully predictable. Coastlines will continue to evolve, not only because of human influence, but also because eccentricity drives long-term sea level fluctuations tied to monsoon intensity, ice accumulation on mountain ranges, and thermal expansion of the oceans. Over tens of thousands of years, even in the absence of global ice sheets, subtle but detectable sea level variations will follow the orbital cycle. Eccentricity's long-pulse influence on ecosystems will continue as well. Rain belts will drift north and south, shaping the biodiversity of tropical regions. The Amazon basin may experience periods of greater rainfall, followed by drier intervals. African savannas may expand and contract. Grasslands across Central Asia, North America, and Australia will shift with changing monsoon strength. And humanity, if still present in its current form, will continue adapting. Future descendants may witness the greening of deserts, the return of megalakes, or the expansion of forests into regions currently barren. They may live in climates that echo distant ages, revived by the orbit's slow march. But the greatest question is not what eccentricity will do. It is how humans will interact with it. For the first time in Earth's history, a species has the capacity to alter climate faster than orbital cycles can. The natural cycle of glaciation, once the dominant force shaping landscapes and migrations, now competes with human-driven warming. Will future humanity choose to remain in a perpetual interglacial? Will they attempt to counteract orbital cooling when it emerges? Will they enhance or mitigate eccentricity's influence through geoengineering? Or will they allow Earth's ancient cycle to resume once atmospheric CO2 returns to lower levels over geological timescales? Whatever choices civilization makes, one fact remains. Eccentricity is not going away. It will continue turning, slow and patient, guiding Earth's seasons for millions of years to come. And if distant future generations ever look back, through ice cores, ocean sediments, or perhaps their own historical records, they will see the same pulse that guided the mammoths, the first humans, the rise of agriculture, and the shifting monsoons of the Holocene. The pulse will be there, steady and unwavering, a celestial heartbeat. As we close this long story, imagine Earth drifting through space, its orbit stretching gently, sunlight shifting across hemispheres like a slow wave. Ice grows, then melts, seas rise, then fall, deserts bloom, then fade, forests advance, then retreat. Life adapts, migrates, evolves, humans build, collapse, rebuild. And through it all, eccentricity turns, quiet, constant, ancient. The world changes, the orbit continues, and Earth, as always, breathes.